Welcome to this explainer. Today, we're diving straight into a cosmic detective story, turning a massive mystery from our galaxy's heaviest star cluster into clear, hard data. We're going to piece together a wild puzzle surrounding a specific extreme group of objects known as PSR J1326-4728 A through R, using radio telescopes, X-ray forensics, and some of the most intense physics in the universe.
So our investigation really kicks off with one big question. What exactly is hiding in the core of Omega Centauri? You see, for years, astronomers were picking up this mysterious gamma-ray signal coming from the region, officially tagged as FLAOI J1326.7-4729. This constant glow of high-energy radiation was a massive clue. It strongly hinted that there were some hidden, incredibly extreme objects lurking in the dark, but we just didn't have the full picture yet.
Section 1. The Omega Centauri Mystery.
Let's set the scene of the crime here. We're looking at a region located over 5,000 parsecs away from Earth. And Omega Centauri isn't just your run-of-the-mill star cluster, it's an absolute behemoth packed with 3.6 million solar masses. Because it's so unbelievably dense, the stars in the core are constantly interacting and passing close to one another. Astronomers call this having a high stellar encounter rate. Basically, this cluster acts like a giant factory, creating the perfect breeding ground for our cosmic suspects, low-mass X-ray binaries, which eventually evolve into something way more exotic.
Moving on to Section 2. Finding pulsars A through R.
After some incredibly painstaking observation, astronomers finally unmasked the source of that gamma-ray glow. They found 18 distinct radio signals, officially designated as the pulsars PSR J1326-4728 A through R. But what exactly are we dealing with here? Well, these are millisecond pulsars, or MSPs. Think of them as the ultra-dense, collapsed cores of dead massive stars that have literally been resurrected. By stealing, or accreting, mass from a companion star, they get spun up to dizzying speeds, sweeping beams of radiation across space, kind of like a cosmic lighthouse.
The way this discovery unfolded is pretty incredible. First, that initial gamma-ray anomaly led researchers to predict a hidden population of roughly 19 millisecond pulsars. Following that breadcrumb, the Parkes radio telescope in Australia managed to find the first 5 suspects, pulsars A through E. But the real breakthrough? That happened when the ultra-sensitive MeerKAT telescope in South Africa turned its eyes to the cluster and uncovered 13 new ones, pulsars F through R. That brings our total to an amazing 18 pulsars.
Now, to really wrap your head around how extreme these objects are, get a load of this number. 1.84 milliseconds. That is the rotation speed of one newly discovered suspect, pulsar J. It completes a full rotation in a fraction of a blink of an eye, making it the fastest spinning suspect discovered in this entire cluster so far. Just imagine an object heavier than our own sun spinning hundreds of times every single second. It's absolutely wild.
Section 3. Meet the spider pulsars. Okay, as we dig a bit deeper into the data, things get a whole lot darker. We realize that many of these suspects aren't just spinning alone in the void. No, they are locked in a deadly cannibalistic embrace, forming what we call spider pulsars. This is a brutal class of binary systems where the pulsar emits a relativistic wind, a literal storm of high-energy particles that blasts its own companion star apart, slowly stripping its material away over time.
The crucial way we distinguish between these predatory systems is actually based on the surviving mass of that poor companion star. On one hand, we have the ultralight black widows, where the companion has been brutally whittled down to less than 5% the mass of our sun. And then we have the slightly beefier redbacks, where the companion still holds on to a mass between 0.1 and 0.5 solar masses.
The MeerKAT telescope actually gave us some incredible specifics on these systems. For instance, suspects like pulsars K and L were identified as classic eclipsing black widows. And what's happening there is fascinating. The shredded, vaporized material from the dying companion star is physically blocking our view of the pulsar's radio pulses at certain points in its orbit. We also caught pulsars G and H locked in extremely tight, rapid orbits that take less than 3 hours to complete.
Section 4. Chandra's X-ray vision. Now, to completely confirm the true nature of these systems, radio data alone just wasn't going to cut it. We had to bring in our heavy-hitting forensics team, the Chandra X-ray Observatory. By precisely mapping our suspect's radio positions over Chandra's deep X-ray exposures, researchers did some heavy cross-referencing and successfully identified confident X-ray counterparts for 11 of the 18 pulsars.
And let me tell you, those X-rays act exactly like forensic fingerprints, revealing two totally different realities. First, you have gentle thermal X-rays. These are just radiating from small hotspots on the surface of the isolated pulsars. But then you have the hard, non-thermal X-rays. These are produced by violent shock waves in the spider systems, occurring right where the pulsar's intense particle wind slams into the strip material of its companion star.
You can actually see this difference plain as day when you directly compare the data. Take the soft, thermal X-ray spectrum of pulsar A, which is an isolated pulsar just calmly radiating surface heat. Now contrast that with the hard, aggressive, power law emission of pulsar B. Pulsar B is one of those cannibalistic, eclipsing black widows we talked about, and that intense X-ray signature, that is the direct result of a violent intrabinary shock.
Section 5. Decoding the cosmic clues.
Bringing all this forensic data together really closes the loop on our investigation into the heart of Omega Centauri. By combining radio timing and X-ray spectroscopy, the true identities of our primary culprits are fully exposed. We've got Pulsar B, our violent X-ray shock emitter. There's Pulsar J, that isolated speed demon spinning at 1.84 milliseconds. We have K and L, the eclipsing black widows hiding behind their own destruction. And of course, A, C, and E, the faint, isolated thermal emitters.
So what does this all mean? Why does uncovering these 18 pulsars matter so much? Well, the researchers summed it up perfectly. These objects are living fossils. Their specific types, their tight orbits, and their aggressive behavior actually encode the violent multi-billion-year dynamical history of the entire Omega Centauri star cluster. They are a literal record of countless stellar encounters that played out eons ago.
And that brings us to the end of today's cosmic detective story, but honestly, it leaves us with one final fascinating thought. If just one ancient star cluster was hiding an entire population of cannibalistic spiders and ultra-fast spinning dead stars, what other monsters are out there? What else do our telescopes have yet to unmask in the deep dark of space? Thanks so much for joining me for this explainer. Keep wondering, keep looking up, and I'll catch you in the next one.